Okay, let's recall that for a m by n matrix A, we have the notion of the, say, null space also known as kernel of A is defined to be the set of all x's xing on n such that ax is equal to 0 as a subspace of Rn. Okay. And the nullity of A is the dimension of the null space. Okay. We also have the range of A denoted by R of A. And this is, by definition, the vectors in Rm of the form y equals to ax for some x. So by construction, it's a subset of Rm, and we've shown that it's a subspace. And the rank of A is the dimension of these range. Also, we note that in fact, if we write A in column forms A1, A2 to AN columns, then the range of A is the span of the columns A1 through AN. So it's also known as the column space of A. Okay. Another thing we have for a given matrix A is that well, we also have the row space of A, which is row space, which is the span of rows of A. Okay. And because rows are n-dimensional vectors, this is a subspace of Rn. Okay. Now, so let's see. Row space. Now let's make the following observation. Row space of A, again, is the span of rows of A. Right now, as you remember, there's this operation that we do to a matrix called the transpose, which is to flip the matrix across the main diagonal, and the effect of that will turn rows into columns. So the rows of A after transpose becomes columns columns of the transpose. So the row space of A becomes the column space of A transpose. Okay. So the dimension of row space of A is therefore the same as dimension of column space of A transpose. And column space of a given matrix is also called the range of that matrix. So this is therefore the dimension of the range of A transpose. And by the definition, this is called the rank of A transpose. Okay, so we have now the notion of rank of A. Before that we had the notion of nullity of A. And then we also have the rank of A. And now we have the rank of A transpose appearing in the discussion. So the first theorem that I want to state is that the row space, the dimension of row space of A is equal to dimension of column space of A. Okay, so this is the statement of our theorem. Now in different terminologies, we've called the dimension of the column space the rank of A, and we just saw that the dimension of the row space of A is the rank of A transpose. So in other words, the statement I made, in other words, rank of A is equal to rank of A transpose. Okay, so we will think about that in a moment. There's one, so that's one theorem. And the next statement is a fact that I'm going to stay for now, not discuss well, for a while anyway. So A here, so let's say A is an n by n matrix as before. Then we have the notion of nullity of A. We also have the notion of rank of A. The statement is that their sum is equal to n. Okay. We've checked this in one example in the previous lecture. You can do this. You can see this in other examples as well. Okay, that we're going to postpone the further discussion of this equality to later. Before we prove this theorem, we're going to discuss some easier statements first. So maybe let's label this theorem as theorem A. And now, moving on. So we have another theorem. Say it concerns linear systems. Suppose you have an n by n system written in the form AX equals to B. And as we've seen before, we are interested in solving the system. So we are in particular interested in knowing when the system has a solution, or in other words, when the system is consistent. Now the theorem gives you a criteria for consistency of the system. It says that the system AX equals to B is consistent if and only if the following equality holds. The rank of A is equal to the rank of AB, the new matrix formed by adding one column to the right end of A. And let's keep in mind that this AB matrix here, this is what we've been calling the augmented matrix. Augmented matrix. And the matrix A, in view of this linear system, is called the coefficient matrix. Okay. So that's again, the content of the theorem tells you that a linear system of AX equals to B has a solution if and only if there's some equality involving the rank of its coefficient and augmented matrices. Okay, this we can fairly easily prove. Now, if we write, as we did before, the matrix A in column forms, A1 through AN, columns, then AX is equal to x1 a1 plus x2 a2 plus plus xn an. So AX equals to B, the system has a solution if and only if you can find, only if you can find this x1 through xn so that AX is equal to B. But this x1 through xn writes AX as a linear combination of A1 through AN. So what this means, having this x's mean that B can be written as a linear combination of the A's. That means B belongs to the span, the span of A1 through AN, which is what we call the range of A. Okay. Now what? Now, note the following. Note that the span of A1 through AN sits inside the span of A1 through AN and B, right? Because the span of A1 through AN just consists of linear combinations of A1 through AN, each of which is a linear combination of A1 through AN and B. Simply put the coefficient associated to B to be 0. Okay, so you can do that. So now what? Because of this inclusion, B, to have B belonging to A1 through AN, the span of A1 through AN is the same as the two spans being the same, right? Because one span is already contained in the other. Now, if the only new thing, the only new vector you add, namely b, also belongs to the span of a1 through an, then this span of a1 through an and b is gonna be inside the span of a1 through an. Therefore, the two spans are equal. Okay. Now, what this means? Now you have two subspaces of Rm, right? And the two spans, they are subspaces of Rm, and they are equal if and only if they have the same dimension, which is the same as the dimension of the span a1 through an equals to the dimension of span of a1 through an b. Now, these dimensions have different names, right? Because the span of the column space here, the span of a1 through an is the range of A. Its dimension is the rank of A. Now, likewise, this span is the column space of the augmented matrix, so its dimension is the rank of the augmented matrix. And that's the proof. Okay, that's simple. Now another theorem is also about solutions to linear systems, but of a special kind. Now, if you have A being a square matrix, say n by n matrix, then A is non-singular if and only if the rank of A is n. Okay. Now, remember, being non-singular means that A being non-singular means AX equals to 0 has only the trivial solution, right? Now again, AX can be written as x1a1 plus x2a2 plus blah 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 plus xn and this below. So what this is saying is that this linear combination equaling 0 has only the trivial solution. So A being non-singular, non-singular, being non-singular, if and only if A1 through AN is linearly independent, right? Being linearly independent means exactly that this equation is only possible when the x is all equal to 0. Okay. Now, since A1 through AN, the columns of A span, span is span, but its span has a different name, the range of A, right? the columns A1 through AN is a spanning set of the range, but it's also linearly independent, so it's a basis. Okay, so that means so being linearly independent means A1 through AN being linearly independent is the same as A1 through AN being a basis of RA, the range of A. Okay. Okay. Now, what do we know? I.e., what does it mean? If you have having A1 through AN being a basis means that the dimension of R of A is N. Right? And the dimension of R of A is the rank. This is the rank of A. Okay, so what we just established is that, well, again, A being non-singular means that this system, so this equation is only possible when x is 0, which is the same as saying that A1 through ANs are linearly independent, which is the same as saying that they form a basis of the range, which is the same as saying that the rank, that is the dimension of the range, is N. And that's the theorem. Okay. Now we should, I should tell you that applying this theorem in practice to a given matrix amounts to, if you have a matrix, you are trying to decide whether AX equals to B or A is non-singular or not. What you're gonna end up doing is to solve some systems. And even if you're trying to use this theorem, you're gonna need to compute the ranks of some matrices, and that amounts to solving some systems. So the essential technique is still solving linear systems. Okay. Now moving on. Okay, now let's prove theorem A. So recall what the statement is. Recall the statement of theorem A is simply saying that the dimension of the row space of A is the same as the dimension of the column space of A. Okay, so we will try to therefore compare these two dimensions. So let A be our n by n matrix and write it be written in row forms. What does this mean? This means suppose we write RA as A11, A12, A1J, A1N, A21, A22, A2J, A2n, AI1, AI2, AIJ, AIN, AM1, AM2, AMN, not AMN here, AMJ, AMN. Suppose we write our matrix A in this form, then this is the ith row. Let's denote the ith row by AI. Okay. So in row form, A is the stack of these rows, A1 through AM. Okay. And the columns of A are here. This circled one is the J's column. Let's call it AJ. In this form, you can also write A in the column form, A1, A2, AN. Okay. Now, the row space. As we already said, row space of A is the same as column space of A transpose. Let's suppose the rank of A transpose, which by definition is the dimension of column space of A transpose, and consequently the dimension of the row space of A. Suppose this rank is K, okay, some number. All right. So suppose this number is K, and we certainly have well, how do I want to write this? The row space of A is by definition the span of these rows A1 through AM, right? And our assumption is that this thing is dimension K. By assumption, there are vectors, K vectors. There are K vectors W1 through WK, which form a basis of the row space of A. Right, we assume the row space has dimension K, therefore we can find a basis consisting of K vectors. And we can write each of these W's as a 1 by n vector. That is, WJ, say, is written as wj1, wj2, wjn. Okay. Now being a basis, you can write everything in the row space of A as a linear combination of the W's. So every vector in row space of A can be written as a linear combination of the basis vector of our choice, W1 through Wk. In particular, those row vectors A1 through AM. Okay, let's pick some notation for that. A1 is, say, C11W1, C12W2, C1KWK. A2 is C21W1 plus C22W2 plus C2KWK, and so on. AM is CM1W1, CM2W2, CMKWK, right? Now, keep in mind that this is an equation of row vectors, right? So on the left side, we have the A's. A1 is A11, A12, A1n. A2 is A21, A22, A2n, and so on. AM is AM1, AM2, AMN, right? On the right-hand side, we have something more complicated. We have, for example, in the first equation, we have C11, W1. W1 is written as W11, W12, W1n plus C12, W, what? 21, W22, W2n, and so on. And likewise, the left-hand side of this, the right-hand side of the second equation is C21, W11, W12, W1n, C22, W21, W22, W2n, and so on. And likewise, oops. And the last equation on the right-hand side is CM1, W11, W12, W1n plus CM2, W21, W22, W2n, plus so on. Now, here's what we're going to try to do. We'll equate the J's component of the two sides right? For example, if J is 2, you would, like in the first equation, we'll be looking at the term A12. on the right-hand side of the equation, we will need to pick up every second component in every term. So that will be the terms, proportion terms here. Now for the second equation, we'll be looking at this component, A22, where on the right-hand side, we'll be looking at W12, W22 again. Oops. W22. Right? And so on. So for the last equation, we'll be looking at AM2 and W12, W22, and likewise. Okay, but if you do this, I mean, each equation, you get equality of numbers. For the same J, you do this for the same J to each of these equations and assemble the outcome as an equality of M tuples. Now you'll get the following. So that'll be a, what is that? So if you do the J's component, you'll be picking up A1J, A2J, down to AMJ on the left-hand side. On the right-hand side, you will be, in the right-hand, each component on the right-hand side is going to be a combination of things, C11, W1J. Oops, no, I don't want to do that. I want to do it differently. They have this, it's going to look like W1J, C11, C21, CM1 plus W2J C11, no, C12, right? C22, CM2, all the way to WKJ, C1K, C2K, CMK. All right. That's what you get by comparing the J's component of the two sides and form an equality. Now, let's now interpret what we get. Each of these is a column vector, is an m-dimensional vector. Okay, so let's call this C, this is some, C1, C2, and CM. Okay, each of the C's, C1 through Cm, are m by 1, m by 1 column vectors. No, C1 through Ck. C1 through Ck. Through Ck, m by 1 column vectors. Okay. Now, over here on the left-hand side, you just have the J's column. As we've seen already, this is the J's column right here. So this is just AJ. This is just AJ. Okay. So what did we do? So this equation is just saying that AJ is a linear combination of C1 through CK. So AJ now belongs to the span of C1 through CK. Okay. That's what this equation is telling us. Now, because this is true for every J, so the span of A1 through AN, each of which belongs to the span of C1 through CK, must actually be inside the span of C1 through CK, right? And the span of A1 through AN is the range or the column space. So dimension, once you have this inclusion, you can compare dimension of the range of A cannot be more than the dimension of the span of C1 through CK. Now, evidently, C1 through CK is a spanning set of the span. Therefore, the dimension or the number of elements you need in a basis of the span is no more than K. This is less than or equal to K. Now what this is saying, that the dimension of the range is which is by definition the rank of A, is less than or equal to K. And let's remember what K is. K is, by our choice, the rank of A transpose. Okay. So what we prove after this discussion is that the rank of A is no more than the rank of A transpose. So the rank, now if you apply the same discussion, the same strategy to A transpose, because this discussion holds for any matrix A, in particular it should hold for A transpose, that will tell you that the rank of A transpose is less than or equal to the rank of A transpose transpose. Now, as we've talked about before, it's clear that by the construction of transpose, A transpose transpose is just A. So this rank is the rank of A. So now we have the rank of A less than or equal to the rank of A transpose and the other way around. So they must be equal. Okay. That's that. Very simple. Okay, so now you're going to think a little bit more abstractly. The next goal is to think about vector spaces or vector spaces abstractly. Okay, so let's first of all recall what we've been doing. We've been doing to Rn Right, we add vectors in Rn. And we scalar multiply. We multiply vectors in Rn by numbers. Right, these are the two operations that we mostly do. We do most often to vectors in Rn, and these operations have nice properties, as we've seen already. Nice properties, right? So now we're gonna basically take this take these and make things abstract. That is, we can consider the following definition. A vector space over a field, a scalar field, K is a set denoted by V that admits two operations. Vector addition, for being first of all, which does the following given U and V, both in the set V. We get some new object U plus V, also an element in V, and scalar multiplication given a vector or given element in V and a scalar or number in K, we get A times U. Okay. So the vector space V is a set that means these two operations, vector addition and scalar multiplication, satisfying the following properties. And the first two properties are just restatement of what we already said. The closure property C1 says that U plus V belongs to V. C2 says that A times U belongs to V. Closure property. Now, properties on the vector addition. Properties of vector addition. Oops. Okay, there are 4 of them. The first one is A1 says that u plus v is equal to v plus u. A2 says that if you have three vectors, u plus v plus w is u plus v plus w. A3 it says that there exists a vector denoted by 0 and called the zero vector such that for any u in V, u plus 0 is still u. Okay. A4, the last property on vector addition, it says that given u in the vector in the space V, there exists another vector called minus u, also in V, such that u plus minus u is the zero vector. Okay. So these are the four properties of vector additions, and there are also four properties of scalar multiplication. Okay. The first one is let's call it M1. Is if you have two numbers A and B, A times B, so A times BU is AB times U. Now M2, if you have two vectors instead of two numbers, you can form U plus V, and A times U plus V is AU plus AV. Now M3 is if you have two numbers again, A times AV, you have A plus B times U, that's A times U plus B times U. And finally, M4, the number 1 here, which exists in K, right, because K is a scalar field, times any vector U is U, or any U, V. Okay, now let's review what we just did. We define a notion of what's called vector space. Abstractly, this is a set denoted by V. This is a vector space over a given scalar field. Okay. This is a set V that has two operations. The vector addition given two, which basically says given two vectors, you can form another vector called U plus V. And the scalar multiplication, which says that you have when you are given a vector U and a number in K called A, you can form A times U, also a vector. And I should probably say it's in V. Now, the two operations are required to satisfy three classes of properties. The first class is called the closure properties, and they're just saying that the two operations produces things still in V. Now, the second class of properties concerns vector additions. For example, U plus V is V plus U, u plus v plus w is u plus v plus w, depending on, it doesn't depend on the order of things. The third property is about the existence of a special vector called 0, such that u plus 0 is u for any u. The next property is about given a u that exists, it's a minus u, so that u plus minus u is 0. Okay. The last class of properties is about scalar multiplications, and there are 4 of them again. One is a times bu is ab times u. A times u plus v is au plus av. A plus b times u is au plus bu. And finally, 1 times u is u for any u. I should probably be more specific here that a, b belongs to k, u belongs to v, a belongs to k here, uv belongs to v, and again a, b belongs to k, u belongs to v. Okay, so we basically define vector spaces as a class of sets, certain kinds of sets with 2 operations endowed on them, satisfying a list of properties. Now, before we go to examples, we'll just make some obvious observations. These properties are the same properties satisfied by addition and scalar multiplication of vectors in Rn. Right? If you compare this previous discussion on vectors in Rn, you see that these properties are indeed properties hold true for addition and multiplications of vectors in Rn. So Rn and its subspaces are all examples of vector spaces over, well, the scalar field in question. As we remember, we've always been multiplying by R, by numbers in reals. So the scalar field here is R. So Rn and its subspaces are all examples of vector spaces over the field R. Okay. So now the next lecture, we will first of all review the definition of vector spaces in general, and then we will move on to look at some examples that are not in Rn.